Good morning, everyone. I hope you're all doing well. Today, I wanna solve a very special problem. It's a theoretical problem actually. In my probability class, I think it's kind of interesting. It's like Taylor series, but a part of Taylor series. It's Taylor series without going to infinity, and we'll see how we connect the summation. Like if you're a math major, you know that this thing and this thing is serious, right? The summation and integration is similar. Sometimes you see engineer or physicists, they exchange the sign, they swap the sign. Like, why would you do that? Like, I feel you. So today I will solve that problem. Okay. So the textbook I'm gonna use is a first course in probability. Okay. Course in probability by Sheldon Ross. Sheldon Ross. Ninth edition. Okay. Okay, and the problem we're gonna solve today, let me write in, is problem 4.26, page 172. If you use PDF, it will be on page 185, our 484. Okay, this is for PDF. All right, what's the problem ask us to? The problem asks us to show that summation, show is similar to proof. Okay, proof seems more manly, more rigorous, more but show that it's like it's the same meaning. So okay, so what do you have to show? The problem asks us to show that summation of I equals 0 to n of e to power lambda times lambda I over I don't know how to say this, factorial, factorial equal 1 over n factorial times integral from lambda to infinity of e to power ex x and dx. Okay, this sounds really interesting, right? This sounds very interesting. Now I'm gonna show you guys how to do this. Okay, so the textbook, they say that the hint is integration by part, right? The textbook gives us a hint. Okay, integration by part. Alright, so then let's follow the textbook hint then. Why not, right? Okay, so I'm gonna go ahead and call this the right hand side, and this the left hand side, or LHS and RHS. Alright, let's do some transformation. Alright, right hand side, what does it equal to, guys? In mathematics, if you don't know what to do, always repeat the problem. So rewrite it. Okay, didn't do any changing, any manipulation yet. Just keep rewriting it. X to power n dx. Alright, now if you recall integration by part, u prime integral of u prime v equal uv minus integral v prime u, right? So now I'm gonna do some changing. Okay, I'm gonna do some manipulation. You recognize that I'm gonna rewrite this rewrite this as you recognize that e to power of negative x is derivative of negative e to power negative x. Okay, does it make sense? Okay, cool. Oh, sorry guys, earthquake. Yeah, gotta run. Actually, it's over. Okay, let's continue. Okay, so according to that, we use this theorem. This is Bay. If this is okay, if you recall, A to B of this, we go to a to b of that, a to b of that. All right, so we will have infinity lambda negative e to power negative e to power negative x xn minus integral from infinity lambda to infinity negative ex, right, times xn prime dx. Okay, does it make sense so far? I'm literally using this. I don't know, this is product rule of integration, I guess, or you know, whatever you want to call it. All right, let's try to simplify this. You see, look, what is this? What is this term equal to? It equal to 1 over, yeah, I don't know what to do. I'm gonna rewrite it. E negative infinity, right, times negative times infinity to the power of n, right, and then minus e to the negative lambda n, all right, and then all that plus, okay, this sign right here come together, create a positive, so negative is positive, so plus go infinity of lambda into infinity of e to the power negative x. What's the derivative of x to the power n? Well, it is n times x to the power n minus 1 dx. Okay, now let's simplify this. E to the power of negative infinity, what is that equal to? It is equal to 0, right? Because let's say you I'm an engineer, so I can told you this. So if you plug in the calculator, you put e to the power negative 999999999, it will be 0. Okay, or you can, another way you can think about it is e to the power negative infinity is 1 over e to the power of infinity. E to the power infinity is a very big number. If you have 1 and you divide to a very big number, you get you 0. Okay, both way it works. Anyway, work for you. Okay, so 0. Okay, so become 0. Okay, minus here is plus, so it will become plus e to negative lambda times lambda n. Okay, plus integral of lambda to infinity e to negative x n minus 1 dx. Alright, I'm gonna void now. I'm gonna go ahead and void it. 1 to the power n factorial times e to negative lambda times lambda n plus 1 to the negative lambda. Okay, now I'm gonna put the n outside. Okay, because n is a constant, or in other words, n is not a function of x. So I'm gonna put n outside. Infinity lambda e to the power negative x negative 1 dx. Okay, so what do we have? We will have equal to e to the power negative lambda times lambda n over n factorial plus, okay, why is 1 over n factorial times n? Recall that n factorial is 1 times 2 times on the way to n, right? So 1 over n factorial times n equal to 1 over 1 times 2 times all the way to n minus 1 times n, right? And then n cancel out. Be 1 over 1 times all the way to n negative n minus 1 will be 1 over n minus 1 factorial. Now I'm right here, factorial times the lambda e to the power nx x and 1 dx. All right. Okay, so this is our RHS, right? So you know, in summary, what do we have? We have all of this, right? Right here equal to RHS. And what's RHS? RHS is this one, okay? So I'm just gonna rewrite it, okay? So we have 1 over 50 n factorial times lambda infinity e power negative x xn dx, okay, equal to 1 over n minus 1 factorial infinity lambda infinity e to negative x n minus 1 dx, okay, plus e to power lambda n over n factorial. All right, now I'm gonna do something very interesting. I'm gonna rearrange it. I'm gonna, okay, like this, 50 e to power ex, a to power negative x times xn dx, okay, minus 1 over n minus 1 factorial times integral from lambda to infinity of e to power negative x to power n minus 1 dx equal to e to power negative lambda times lambda n to power n over n factorial. Now I'm going to do something very interesting, okay? I'm going to say this term equal to fn. So this term right here, you can observe it will become fn minus 1. Okay, and I would say I will call this term right here gn. Okay, do you see it? Because if you replace n with n minus 1, you get this term, right? Assume it's a function of n. So we have what? We have fn minus fn minus 1 equal to gn. Okay. Okay. Now I'm gonna do something very interesting right here. It's kind of intuitive, but it will make sense, I promise. I'm gonna do something called recursive analysis. So recursive. I'm gonna, so that it generate a bunch of geometric series, I guess, and then things cancel out. You know, like they always say, things cancel out. In the end, everything will be fine. Okay, so this is a continuous equation 1. I'm gonna rewrite like this: fn minus 0. Okay, I'm gonna write this in red. Equal to fn minus. I'm gonna put it like this. Put this like this. N minus 0 plus 1 equal g n minus 0. All right, so now I'm gonna keep going. So f n minus 1 equal to f n minus 1 plus 1 equal to g minus n minus 1. Okay, on the way. Okay, 0. Okay, this is 0, this is for 0, this is for 1, on the way. Okay, that to n minus 1. Okay, so what do we have? F n minus, okay, now I'm gonna put a bracket, n minus 1 minus f of n minus 1. I have to write in red because so you guys can see the main character right here. G n, I forgot a bracket, minus, I have to put a lot of bracket, n minus n minus 1. All right, okay. Now all right, so what does it mean? It means that, you know, you think things start to cancel out, right? If you okay, if you add all of them together, okay, if you add all of them together right here, okay, so what will you notice it's gonna cancel diagonal, so this term and this term cancel, right? And then this term I suppose this one cancel out, then this cancel, then this one cancel, and then left for this one. So if you add all of them like that, you have f of n minus f of n minus n is f0 equal to on this way add is chi n, plus chi n minus 1, okay, plus on the way to chi 1, right? So what's fn? So fn equal to f0 plus t1 plus t2 plus on the way to tn, okay? Okay, now I'm gonna rewrite in the normal term. So what is fn? What's our f? fn is this, okay? 1 over n infinity integral. Wait, is it the integral or? Yeah, it's the integral. So integral from lambda to infinity e to the power ex what, let me see, sorry, xn dx equal, okay, what's f0, guys? What's f0 is this times lambda to 50 x, right? You remember this f0, this fn, okay? Okay, and then what is chi1, chi2 on with chi would be, what is chi? Chi n is eternal x, okay? So it would be eternal lambda times lambda 1 over 1 cube 1 factorial plus e to lambda negative lambda times lambda to the power of 2 over 2 prime factorial plus on the way to times lambda n minus 1 factorial, and plus e to power lambda times lambda n factorial. All right, okay, let's see what I can simplify and what can I write in a better form. Okay, the left hand side I don't know what to do, so I just keep on rewriting it. Guys, if you have a chance, always simplify your expression. 1 over 0 factorial, 0 factorial is 1, 1 over 1 is 1, x to the power 0 is 1, so this only left x dx. Okay, and this is the summation, like, okay, this is a summation. Can I write in a geometric form? Of course I can. It is a summation of e to the power negative lambda times lambda I, okay, I is not a complex number in this case, okay, guys? I not complex number. Not complex. It's not the imaginary I. That we know. I is a real number. Okay.